going to be surface area of a volume of revolution. In other words, do you remember those volumes where we took a region and rotated them around a line from section 7.2 and 7.3? Well, you know how to find their volumes. Now I want their surface areas. Okay, so we are going to approach this in the same way. I'm going to have some odd-shaped shape. I'm going to slice it up and find the surface area on the slice. Okay, now, how am I going to do this? Well, imagine trying to find the surface area of a human. Okay, what I would do is basically take paper and cut it into pieces and cover you with that paper, and then find the surface area of the paper. Okay, now the most common shape we need, okay, is actually going to be based on a cone. Okay, specifically, it's going to be a cone with its top cut off. Okay, so our goal is to figure out the formula for this cone with its top cut off. But before we get to it, let's talk about the cone itself. Okay, all right, so what are the interesting dimensions on a cone? We're going to have the radius here, and we're going to have the length of what's called the lateral side. Okay, now, have you ever made a cone with paper? We were totally going to do this in class, by the way, right? How do you make a cone out of paper? A funnel out of paper? You kind of roll it up at an angle, right? So imagine if I were to cut straight down one side of this cone and unroll it, what shape would I get? Well, I'd get part of a circle, right? Because if you glue these two sides together, it would form that cone. Okay, now the L, okay, well that's what I cut along, so that's this side, so it actually turns into the radius of the circle. Okay, we're also going to have the angle that this is open to, and you're like, wait a minute, where did the radius go? Oh yeah, okay, well, the radius here actually somehow kind of translates into the circumference of this sector. This is called a sector of a circle, by the way. And the formula for area of a sector is 1/2 radius, and remember the radius of our circle is L, times theta, the angle that makes the sector. Okay? All right. So, we need to figure out what theta is. Okay? Notice, please, okay, that the circumference of the base of my cone was 2 pi r, and that turned into the circumference around this sector. Okay, the arc length formula of a sector is the radius of the circle times what angle it is open. So I'm using a whole lot of trigonometry formulas, and no, you're not responsible for reproducing where these came from. So my angle is 2 pi r over L. And I'm going to take this and plug it back in to here. Okay. So the area of the sector, 1/2 L squared times 2 pi r over L. Okay. One of these L's cancels with one of those. The 2 cancels with that 2. And I'm left that the area is L pi r. Okay. Traditionally, I write pi RL. All right. Whew. But remember I said I wanted a cone with a top cut off, and this is a regular cone. So, we want only the bottom half of the cone. All right, you're really testing my artistic abilities here. Okay, so how do we do this? We take a cone, and we cut off the other cone. Okay, let me draw some dimensions. The radius of this circle I will call R2. The radius of this circle I will call R1. I'm going to call this L1. And this L, because that's the actual L that I want to have left alone. Okay, now imagine taking this cone that's divided into 2 halves and slicing straight through it. Okay. and also slicing down the middle. And you're going to get down the middle a right triangle with another right triangle sitting inside it. Here's the R1, the R2, the L1, and the L. Okay. Whew. All right. So remember, we wanted the area of the surface area of this bottom portion of the cone. Well, it'll be the area of the big cone. Okay. Using this formula, pi times the radius of the big cone, otherwise known as R2, times the lateral side length of the big cone, known as L1 plus L, minus pi times the radius of the little cone, the one I cut out, times the lateral side of that cone. Okay. In other words, my area is pi times, let's make sure I do this right, R2L1 plus R2L minus R1L1. Yes. Okay. Now, I'm going to go to this. This is similar triangles. So from the top triangle, L1 over R1 must equal, from the bottom triangle, L plus L1 over R2. Cross multiply gives me this. Okay, do a little subtraction. Says that R2L1 minus R1L1 equals R1L. And you're like, why do I care? Because R2L1 minus R1L1 was part of my formula. So I'm going to plug that in. Okay, I now know that's R1L, and I still have the R2L. Okay, so in total, my area of the surface of revolution is pi R1 plus R2 times L. Okay. Whoo. You with me still? We're not quite done. Now, remember, this is a slice, and then we take a limit as the slices get smaller and smaller and smaller. Well, as the slices get smaller and smaller and smaller, this L gets smaller and smaller and smaller. Namely, R1 and R2 get closer and closer together. So I'm going to let R just be the average of these two radii. Okay. So in other words, twice R is R1 plus R2. Plug that into here. And my area of the surface of revolution becomes 2 pi RL. Oh. Do you like that? Do you want to do that on every problem for yourself? No. So we're going to break one of Dr. DeWitt's absolute cardinal rules. I'm going to give you formulas to write down and just always use the formulas. That's how bad these are. Okay. Whew. All right. So there are 4 variations. Okay. For surface area of a surface of revolution. I'm going to write them all down, and then I'm going to tell you how to decide when to use each one. And you're like, I thought our formula was 2 pi RL. It is 2 pi RL, otherwise known as arc length. Surprise! You're like, this was not a good surprise. I agree. Okay. It is very critical that you are careful of your A's and B's here, or excuse me, of your X's and Y's here. Because it may look like I'm writing the same thing, and I'm not. Sometimes I'm writing dy dx, and sometimes I'm writing dx dy. Okay. All right. So, when do we do these? I'm going to use the first 2 if my region was found by rotating around the x-axis. Okay. I'm going to use the second 2 if my region or my volume was found by rotating around the y-axis. And I'm never going to give you one that doesn't rotate around either the x or the y-axis. Okay. Now, within those 2, your choices are, well, I'm going to use this one if the function is defined as y equals f of x, and this one if it's defined as x equals g of y. Okay. Similarly down here, this is the y equals f of x1. This is the x equals g of y1. Okay. Whew. Okay. Do you hate them yet? Okay. So, in other words, what should you do? You should copy this exactly onto your cheat sheet. Formulas and when to use each one. Yeah. Okay. Example time. It feels really weird to be sitting here talking to myself, by the way. I don't like it. Okay. Rotated around the y-axis. All right. So, first of all, it said rotated around the y-axis. Okay. That means, okay, I'm using one of the bottom two equations. Second of all, this is x equals something in terms of y. So that means the formula I'm using is the very last equation. And I simply hope it somehow works out. Traditionally, the only way to get it to work out is if you miraculously get a u sub to work. Okay. The one thing I'm going to do before I go to the integral is compute what this dx dy is. Okay. Dx dy, that is the derivative of the equation. Well, I have a chain rule. It's 1 over twice the square root times the derivative of the inside, which puts a -1 on the top. So now I plug into my formula. I'm integrating from 0 to 1. 2 pi times my equation times the square root of 1 plus this thing squared. Well, when I square this, what do I get? Well, -1 squared is 1, 2 squared is 4, and a square root squared cancels. Okay. And then dy. All right. First of all, there's absolutely no reason to have two square roots multiplied together when one will suffice. So inside a single square root, I will FOIL these, and I will get 1 minus y plus 1/4, otherwise known as the square root of 5/4 minus y. Sweet! I don't even need a u sub. I can just handle this. Okay. The 2 pi comes along for the ride. 5/4 minus y, I'm basically treating like y. So it becomes to the 3/2 exponent, divide by the exponent, and I have to divide by the derivative of the inside, which puts a -1 out in front, evaluated from 0 to 1. This gives me a 5√5 minus 1 over 6 pi. Oh. Do you fondly remember the days when I just ask you integrals that use power rule? Yeah. Okay, I have one more example for you today. All right, so first thing is to decide our equation. So I'm rotating around the y-axis, so it's one of the bottom two, but I gave you an equation of y in terms of x, so it is the third equation on the list. By the way, literally writing down the correct equation to use like this will earn you points on the test. Okay. All right, as is always the case, I'm going to compute this derivative first. Okay, so this is a 1/3 x to the minus 2/3. Okay. All right, so my surface area is the integral from 1 to 2 of 2 pi x times the square root of 1 plus this derivative squared. All right, well, 1/3 squared is 1/9. X to the minus 2/3 squared is x to the minus 4/3. Because rules of exponents say you double when you square. All right. Now, this is a common trick with surface area integrals. Okay, I'm going to write this as a single fraction. So in other words, I'm going to multiply this 1 over here by a 9x to the 4/3 over 9x to the 4/3. Okay. And then I get 9x to the 4/3 plus 1 on top of that. Okay. All right. Now, rules of square roots says I can do the numerator and denominator separately, which is nice because since the denominator doesn't actually have any pluses or minuses in it, I can actually take its square root. Okay. Then I can combine the number parts to give me 2/3 pi, and the x parts, x divided by x to the 2/3 gives me x to the 1/3. And you're like, that doesn't look all that much better? Only it is. Oh, it is. Because this I can solve with a u sub. U will be that 9x to the 4/3 plus 1. So du will become 12x to the 1/3 dx. All right. It's just easier for me to move the 12 over entirely because I have the x to the 1/3 in the dx. It is a definite integral, so when x equals 1, u will be 9 plus 1 gives me 10. When x equals 2, okay, u will be 145. I had a little help on that one from the calculator. So this integral turns into the integral from 2 to 145. 2/3 pi is still there. The x to the 1/3 dx becomes 1/12, and then square root u du. Okay. All right, so these combine to give me pi over 18. Antiderivative square root of u is u to the 3/2 divided by 3/2. Plug in 2 to 145. Gives me a result of this. Do you see why we hate these so much? Yep, I agree. Okay. All right. So, we had 2 applications today. We learned how to take the arc length, and we learned how to take surface area. Arc length, we do slices again, mostly, and then mostly revert to the formula that my arc length is this. Okay. Surface area of a volume of revolution. I gave you 4 different versions of the equation, and you have to figure out which one fits. Okay. All right, so I'll remind you one more time. This is the last time I'm going to pre-record the lectures. From now on, I will be doing the lectures live over Zoom at regular class time, Monday, Wednesday, and Friday. So I will see you all next week.